Now that we've seen how to calculate probabilities for the continuous uniform distribution, we're going to do the same for the normal distribution. So if x, our random variable, is distributed normally, it is denoted by x tilde with a capital N, with the arguments being mu, the mean, and sigma, the standard deviation. And then we'll wrap things up with standardizing a normally distributed random variable to create the standard normal distribution, which is denoted by z followed by a tilde to indicate that the random variable has been standardized, and this newly created variable in the standard normal distribution has a mean of 0 and a standard deviation of 1. So the normal distribution describes random outcomes that are symmetrically distributed around the mean, just like the uniform distribution. However, unlike the uniform distribution, outcomes closer to the mean are more likely than outcomes that are further from the mean. As previously noted, we indicate that the random variable x is distributed normally by x followed by a tilde with a capital N, where the arguments for the normal distribution are the mean, mu, and the standard deviation, sigma. The PDF is a bell curve where essentially all the outcomes lie within three standard deviations of the mean, or in other words, the chance that x falls within the range of 3 standard deviations below the mean to 3 standard deviations above the mean is greater than 99%. The CDF calculates the area underneath the bell curve and can be accessed in Excel by typing in equals norm.dist, where the arguments for this function are the value of x that you want to evaluate the CDF at, the mean, mu, and the standard deviation, sigma, of the distribution, followed by a 1. The 1 in the last argument tells Excel to use the CDF and not the PDF. You can also type the word true in all caps in place of the 1. The normal distribution is by far the most important distribution in statistics and will be the foundation for all the statistical analysis that we'll be doing this semester. So as I said before, the PDF looks like a bell curve that's centered on the mean mu, with virtually all observations lying within 3 standard deviations of the mean. PDF is an S-shaped curve that starts at 0 and initially increases at an increasing rate until it hits a point of inflection at the mean, where it begins to increase at a decreasing rate. The result is an S-shaped curve. Keep in mind that this distribution is symmetric, with 50% of the observations lying below the mean and 50% of the observations lying above the mean. Returning to our 3 types of events for continuous random variables, let's assume that we have a random variable x that is distributed normally with a mean of 75 and a standard deviation of 8. So the PDF for this random variable looks like the following bell curve. Returning to our first type of event, the probability that x is less than some value, we're going to calculate the probability that x is less than 85 for this example. To do that, we're going to evaluate the CDF at 85 by typing into Excel equals norm.dist, open your parentheses up, type in 85, comma, the mean 75, comma, the standard deviation of 8, comma, and a 1 for the CDF, and close the parentheses. Hitting enter will reveal that this probability is 89.44%. Our second type of event is the chance that x is greater than some value. Again, we're going to use the example of the probability that x is greater than 60. As we saw previously, this is equal to 1 minus the CDF evaluated at 60. To calculate this, we type in Excel equals 1 minus norm.dist, open our parentheses, enter 60, comma, 75 for the mean, comma, 8 for the standard deviation, comma, 1 for the CDF, and close the parentheses. And we see that this probability is 96.96%. And then our last type of event is the chance that x falls between two values. In this example, we're going to calculate the probability that x is between 60 and 85. As we saw previously, we're going to calculate, as we saw before, we're going to evaluate the CDF at 85 to calculate the chance of getting less than 85, and subtract from that the CDF evaluated at 60 to get the remainder in the middle. To do this, we just type in equals norm.dist evaluated at 85 and subtract from that norm.dist evaluated at 60 to get the 86.4% that we see. Now, what if we want to know what value defines a certain percentile? In other words, it's possible to determine the critical value of x, where x is a normally distributed random variable that defines a given percentile. That is, the probability of getting an x less than this critical value equals that percentile. To do this in Excel, we just type in equals norm.inv for inverse. And in this case, we provide the probability that we're looking for, and it's going to return the x associated with that probability. So equals norm.inv, the percentile that we're looking for, comma, the mean, comma, standard deviation, and then close the parentheses. So again, let's assume that x is normally distributed with a mean of 75 and a standard deviation of 8. If we want to know what value defines the 90th percentile in this distribution, we simply type in equals norm.inv 0.9 for the 90%, comma, the mean of 75, comma, the standard deviation of 8, and hitting enter will reveal that the value is 85.252. Turning our attention to the standard normal distribution, it's important to note that any normally distributed random variable x can be standardized. Using our formula that we saw previously, where we just take the value of x and subtract the mean to get the deviation from the mean, and then divide it by the standard deviation to create a z-score. So when x is normally distributed, the z will also be normally distributed, and it will have a mean of 0 and a standard deviation of 1. The CDF in Excel can be accessed using equals norm.s.dist, where the .s indicates standard normal, and in this case, the only thing you have to provide is the z that you're looking for, followed by a comma and a 1 to use the CDF. The .s in this function tells Excel to use 0 for the mean and 1 for the standard deviation. So it has fewer arguments than equals norm.dist. And it's important to note that while there's an infinite possible number of normal distributions that can exist out there, they can all be standardized this way. The standard normal distribution is a way of mapping to any of these unique normal distributions. So let's take a look. Returning to the three types of events that we calculate probabilities for, continuous random variables. Let's again assume that we have a random variable x that is normally distributed with a mean of 75 and a standard deviation of 8. We previously saw the PDF distribution for this variable. Now we're going to apply the formula for our z-score and standardize this normally distributed variable. As you can see below, the standard normal distribution with the mean of 0 lines up with our normally distributed variable with a mean of 75. And the standard deviation of 8 with our normally distributed variable has been converted to a value of 1. So every time x increases by 8, z is increasing by 1. Returning to our first type of probability where x is less than some value. If we want to calculate the probability that x is less than 85, we can first standardize the value of 85 by subtracting the mean 75 and dividing by the standard deviation of 8 to find the z-score of 1.25, and typing in equals norm.s.dist evaluated at 1.25 will reveal that the probability of that happening is 89.44%. We next look at the second type of event where we calculate the probability that x is greater than some value. In this example, we're going to calculate the probability that x is greater than 60 by standardizing the value of 60, that is, subtracting 75 from 60 and dividing it by 8. We create the z-score of negative 1.875. And we see that the probability that z is greater than negative 1.875 can be found by typing in equals 1 minus norm.s.dist evaluated at negative 1.875 in Excel. Hitting enter reveals that that probability is 96.96%. And our last type of event where we calculate the probability that x falls between two values. In the example here, we're going to calculate the probability that x falls between 60 and 85 again. Using the standardized values, we see that the chance that x falls between 85 and 60 is the same as the probability that z lies between negative 1.875 and positive 1.25. So we're going to evaluate the standard normal CDF, norm.s.dist at 1.25, which will give us the blue shaded area, and subtract from that the CDF evaluated at negative 1.875, that is norm.s.dist, negative 1.875, to get the area left in the middle, which equals 86.4%. Similarly, we can find out what standardized value defines a certain percentile by using the equals norm.s.inv function and providing the percentile. So again, we're talking about a z that's normally distributed with a mean of 0 and a standard deviation of 1. To figure out what value defines the 90th percentile, we simply type in equals norm.s.inv, with the argument being 0.9 for the 90th percentile, or a 90% chance of a value being less than that, and hitting enter will reveal that the z-score is 1.282, which we see lined up with our x variable above in the graph to the right. Or in other words, 85.252 is 1.282 standard deviations above the mean, and 90% of the values lie below that. So returning to the empirical rule, recall if we have data that have come from a normal distribution, so we have a bell curve centered on mu that tapers off towards 0 at 3 standard deviations away from the mean. We previously saw that 68% of the observations lie within 1 standard deviation of the mean. Another way to say that is that if data are normally distributed, then 68% of the standardized values should be between negative and positive 1. Or in other words, f of 1 minus f of minus 1 will equal 68.26%. You can verify this in Excel by typing in equals norm.s.dist evaluated at 1 minus norm.s.dist evaluated at negative 1. If we go out 2 standard deviations, then 95.44% of the observations should have a standardized value between negative 2 and positive 2, and 99.73% of the observations should have a z-score between negative 3 and positive 3. That concludes our discussion of continuous random variables. The next topic that we're going to discuss is going to be sampling distributions and confidence intervals.